Okay. So we'll start with the test bench for introduction to the sequential circuits, and we'll start with the test bench for sequential circuits. Okay. Uh, so uh, just first introduction to sequential circuits. My screen is visible, no? Okay. So just first we'll see the D flip flop. Okay. First we'll see the D flip flop. Okay. So if you see the D flip flop, this is my D flip flop. So you have the input. Let us take. Input is D underscore in, and output is Q, and next this one is Q bar, and you have the clock. Okay. So this is basic D flip flop. Okay. So basic D flip flop, the operation also we already seen. Okay. So how to write the code for this D flip flop? So I'm writing the RTL code for D flip flop. So first module. So my module name D underscore flip flop, D underscore flip flop, and next input. Okay, input. So input clock. Okay, input clock, and next one more reset also we can add. Okay, so here one more reset. So one more reset circuit is there that we can add. Okay, so here I am using reset. Okay, so input clock reset. Okay, again d underscore in d underscore in uh, and output is what output reg q and q bar. Okay, q and q bar. Okay, so I'm using like always at the rate passage of clock, always at the rate passage of clock. um, so begin. Okay, if reset, that means what? If reset equal to 1. Okay, so begin. Q is non-blocking with what? 0, and q bar is non-blocking with 1. Okay, end. Is it fine? If reset equal to 1, we are resetting the output of the flip flops. Okay, okay, and else begin. Okay, q is initialized to what? So q is non-blocking with the d underscore in, whatever that d input is, that is coming to the, yeah, q, and q bar I can write as not of q. Okay, uh, q, okay, not of q, and q bar is not that much important. Main important is q only. Okay, so end. Yeah, it's needed. Reset equal to, which if reset equal to 1, we need to reset the design first. Yeah. If reset means what? If reset is true. Yeah, reset. If reset means what? No need to give reset that is logical equal to 1. So by default, the compiler will take if reset. Okay. Suppose like if reset equal to 0 means I need to give if not of reset. Not of reset I need to give. Okay. Like this we need to write. Okay. And so this is actually resets are two types are there. So this is what means synchronous reset, synchronous reset, and again these are two types: active high and active high and active low. Okay, so synchronous reset means when it is going from reset mode to functional mode, that is synchronous with the clock. Okay, again it is going from functional mode to reset mode also, that is depending on the clock, that is synchronous with the clock. Okay, is it fine? Both it is functional, going from reset mode to functional mode, or functional mode to reset mode, both are synchronous with the clock. And if you are giving, if reset means this is active high, So when it reset equal to 1, active high, and when reset equal, if we are giving not of reset means this is active low. Okay, and one more asynchronous reset is there. Asynchronous reset means how to write. So same initialization we can use. Okay, you have one more asynchronous reset. So asynchronous reset. Uh, Again, these are two types: active high, and active low. Okay, active low. Okay, so in asynchronous reset, when it is going from reset mode to functional mode, this is synchronous with the clock. Okay, synchronous with the clock. When it is going from functional mode to reset mode, this is independent of clock, asynchronous with the clock. Okay, asynchronous with the clock. Okay, mostly where we are using in industry, we are using asynchronous active low reset. So sometimes if you want to reset your design, okay, sometimes clock will not work. What you can do, you can't reset your design, no. So that's why you need to use asynchronous. That too active low. Active low means what? When reset equal to 0, then you are operating in reset mode. Okay. So that means when power is off, you are operating your device in reset mode. Okay. So active high means what? You are giving the power uh, to operate this one in reset mode. Suppose your mobile phone is there. So mobile phone is switched off. So that means it will go into reset mode when the power is on or off. So that means you need to use this is asynchronous active low reset. Okay. So how to indicate means here. So if it is active high means always at the rate passage of clock, always at the rate passage of clock, or this is sensitivity list, no, or passage of reset, passage of reset. This is active high. Active low means always always at the rate passage of clock, or negate of reset, negate of reset, like this you need to use. So that means here begin how to check if passage of reset. That means if reset q is non-blocking with what? 0. Else q is non-blocking with d underscore in. Okay. Enter and end module. Okay, like this you need to write. Okay, here what you need to do, here here you need to write begin if not of reset, not of reset, q is non-blocking with 0, otherwise else. Hello. Q is d in. Okay, d underscore in, end and end module. Hello, switch off the bluetooth. Hello, switch off the bluetooth. Bluetooth is on. uh, Hello. Yeah, is it fine? Yeah, yeah, I'm audible. Okay. Okay, okay, sure. 2 minutes. Okay. Yeah, yeah, yeah. Okay. So this is my design. And next, coming to the test bench, I need to write the test bench. Okay. So here, if you see, I need to write the test bench for D flip flop. Okay. So here, test bench. So test bench is same as combinational circuit only. Just one more step will be added. That is, you need to generate the clock. Okay. So module D underscore flip flop. Module name is underscore TB. Okay. So why you are writing the test bench? To verify the design. Okay. Step one, declare the internal variables. Declare the internal variables. Okay. Internal variables. So here, yeah, reg clock, next reset, and d underscore in. Okay. And wire q, yeah, q and q bar. Okay. And next, what is step two? You need to instantiate. Okay. Instantiate the design, whatever the design is there in your test bench. Okay. In the test bench. Okay. So how to instantiate my design name? What is my design name? D underscore flip flop, no? D underscore flip flop. Yeah. So design name followed by instance name. So D underscore flip flop, and my instance name is DUT, and I'm using connection by order. Connection by order with connection by position with order list. Okay. So clock reset. How you declare the inputs and outputs? The same order you need to follow. Okay. Q and Q bar. Okay. In the design, how you declared the inputs and output, the same order you need to follow. So how you declared clock reset d underscore in q and q bar, the same order you need to follow in the connection by position with order list. Okay. So this is connection by position. Connection by position. Okay. So connection by position with order list. Okay. And what is step 3? Initialize the reg variables. Yeah, initialize the reg variables. The reg variables. Reg variables. Yeah, so I'm writing begin. Initial begin. So I told you, like, yeah, you need to use concatenation operator. Clock reset d underscore in that is equal to 0 and end. Okay, end. And step 4 is you need to generate the clock. Okay, step 4 is you need to generate the clock. Okay, generating the clock. Generating the clock. Not required. Here you can use always hash 5. Hash 5 is the delay. Okay. Clock equal to what? Not of clock. Clock equal to not of clock. Means what? So that means your clock is off for five time minutes and on for 5 time minutes. 5 nanoseconds. Let us take 5 nanoseconds. What is the time period for the clock? 10 nanoseconds. 10 nanoseconds. You are generating the clock with 10 nanoseconds. Okay. So that is generation of clock. Generation of clock with 10 nanoseconds. Okay. Clock with 10 nanoseconds. Okay. And next, what is step 5? Driving the stimulus. Step 5, you need to driving your stimulus. Okay. To the design. Okay. Driving your stimulus. Okay. So I'm writing initial begin. Okay. You can give like hash 10 also, or you can use like at the rate negate of clock also. Why? Because you are not giving passage of clock means in HTA, static timing analysis, you have some you studied about this setup time and hold time, no? Have you studied setup time and hold time and violations? So in order to overcome that, what we are writing means, so that means the transition should come at neg edge of clock, neg edge of clock, at the red neg edge of clock. First you are applying the reset. Okay, reset equal to what? 1. Okay, and so first you need to reset your design now. So you are applying the reset. Okay, so you are giving the test cases only. Okay, neg edge of clock, neg edge of clock, reset equal to what? Reset equal to 0. Okay, in place of neg edge you can give the delay also. Suppose hash 10, you can give the delay also. Okay, it will take. Okay, so in place of this you can give this one, or at the rate neg edge of clock. Okay, next what I am doing, what I am giving, at the rate, neg edge of clock, neg edge of clock, first I am applying d underscore in equal to what? 1 tick binary 1. Okay, after this, at the rate neg edge of clock, neg edge of clock, d underscore in, equal to 1 tick binary 0. End and end mode. Did you understood the test bench for D flip flop? Okay. Remaining flip flops, SR flip flop shall I tell, or you will try? Yeah. Oh, okay, okay. So that means here, so SR, you need to write SR and D. D we already completed. JK and T. You need to write the test bench, and you need to verify your design. Okay. So you can see in the Vivado, no? Okay. Shall I show in the Vivado or you will try? You will try. Okay. So this is about the test bench for this flip flop, and next class we'll see the shift register. Okay. Okay. So just you try this. Tomorrow we'll see the shift registers. Okay.